Okay, folks, we can get going. Any questions for anyone before I get into content? There was one bug in lab last week that I need to just take a minute to go over because I could not contrive a better teaching moment than this bug that we saw. It's perfect. So the bug was the following. The group in question hooked up the microcontroller to the motor, and they ran the PWM demo code to just spin the motor at some constant rate. And what ended up happening is they would turn the system on and the motor go beep, 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 and twitch like this. Let me tell you what the solution was and see if anybody can guess what the issue must have been given the solution. The students had the oscilloscope probes, the two probes, hooked up to both sides of the optical isolator. So one probe was grounded to the microcontroller looking at the PWM output of the microcontroller. The other probe was grounded to the power supply looking at the other side of the optical isolator to confirm that the PWM was making it through that optical isolator. The solution was, if they unplugged either of the probes, it just started working. What was happening? They were sharing a ground. So they had created a ground path from one side of the optical isolator, the noisy side with the motor. A path existed through the oscilloscope, because remember the two ground alligator clips on the two probes are internally shorted in the oscilloscope, which means if you connect one of those alligator clips to ground, the other probe is also grounded to the same ground that you've connected that alligator clip to. So they created a ground path from the noisy motor side of the circuit through the scope to the ground of the microcontroller, and there was a sufficient amount of noise on that microcontroller ground to reboot the microcontroller over and over and over again. So you unplug one, the noise goes away, and it just runs beautifully. That is perfect. Bruce? Any other good bugs? Most people getting it working at this point. It seemed in lab like most people were pretty much under control, but man, it's hard to build this stuff and have it work. Okay, so let me just remind you then what we've been doing. We've been talking through how to implement a feedback controller for this pendulum. And as I've said in the last few lectures, this has led to a few conversations. The first one about how we get data off the sensor. That's an I2C conversation. The second conversation we had was how we turn that raw data, the accelerometer measurements of acceleration, the gyro measurements of angular rate, how we turn that into an estimate for arm angle by way of a complementary filter. Last lecture, we started talking about the PID controller, being the piece of this system that takes the error between where the arm is presently located, as estimated by the complementary filter, and where we would like for it to be, as specified by the user, and converts that error into a control input for the motor to drive the whole system towards its desired orientation. And our last conversation about PID controllers was very qualitative. I wanted to introduce it largely as sort of an input-output system. If you turn this knob and watch the system, you'll see it do the following, right? So we talked about how, for instance, if you turn up your proportional gain, you'll see your arm get less and less and less steady state error, but then you turn it up too far and it'll start to oscillate. You turn it up too far and it'll go saturation off, saturation off. And we talked about how a tuning strategy that you might deploy for this lab is to start with only proportional gain and turn up that proportional gain until you start to see oscillation, and then add some derivative gain. And the reason that the derivative gain is helpful once you start to see those oscillations is, as we talked about, the derivative term of the PID controller is resisting changes in error. And so when it sees the error changing rapidly, we're rapidly approaching the desired angle, the derivative term of the PID controller fights back against the proportional integral terms of the PID controller to slow the system down. So it increases stability at the cost of speed. But then what we talked about is even with proportional control and derivative control, so you have a relatively snappy but stable system, you will, for this system, inescapably have some steady state error. So if you commanded the arm to here, you'll be dangling here or something. And the only way to get rid of that steady state error was to add a small amount of integral gain to your PID controller. So the conversation last time was very much qualitative. When you turn this knob, here's what the system does. When you start to see this, you can turn this knob and you'll observe this about the system. What I would like to go through today is talk through that tuning process, but substantiate some of that qualitative discussion with the actual math that's underlying this to hopefully, further justify the intuition that we developed in lecture here on Monday and that you'll develop in the lab by playing with this system, okay? So that's the plan. So let me just briefly remind you that this is the system in question. I've modified this block diagram just a little bit for purposes of our conversation today, but we have some pendulum, and 1,000 times a second, we're using our sensor along with an estimator to get an estimate for the pendulum's current position. We're comparing that position. We're subtracting it from the desired hover angle to develop an error in degrees or radians or whatever units you happen to choose. That will go into our controller, the topic of conversation today. The output of that controller is going to be a PWM duty cycle, some number between 0 and 5,000 that's used to set the PWM duty cycle. That goes into our motor. We're going to talk about this block first today, but the motor is a thing that takes as an input some PWM duty cycle and as an output generates a motor rate, a speed at which the propeller is spinning. And the first thing that we're going to talk about today is that transfer function. How does the motor actually translate some PWM duty cycle into a motor rate? Once the motor's spinning, we could imagine there sort of being a second block here that represents the physical arm as a pendulum. The physical arm as a pendulum, we could think as another input-output system that takes as an input some motor rate. That spinning motor generates some thrust, which generates some torque to lift the arm. Pendulum physics occurs. The arm will change its position. We'll sample that position, use our estimator to estimate it, and close this loop and do this again 1,000 times a second. So what I'd like to focus on first of all, in order to develop this controller, we'd like to develop some understanding of the physics going on here. So we're going to talk about the motor physics, and then we're going to talk about the pendulum physics. But let's start with the motor. And what we'd really like to develop is, like I said, the transfer function, the equation that translates the input voltage, or PWM duty cycle, to some motor rate. So in order to do this, we have to come up with a system of equations that models the motor. And we're going to do this by combining the equations for two different sort of representations of the motor. We can think about the motor as a mechanical system, right? The motor is some shaft, and at the end of that shaft, there's a spinning mass, a propeller in our case. Something is torquing that shaft. We'll have a conversation about the actual source of that torque, but for now, if we could just consider the motor a simple mechanical system, you can imagine we're torquing some shaft with something stuck on the end of it, a propeller, and as this thing rotates, we also experience friction that resists that motion that is proportional to the speed at which the motor is rotating. So we're applying some torque to the shaft. There's a mass at the end of the shaft with some moment of inertia, J, and as this thing rotates, we experience friction that's proportional to our speed of rotation. As we spin faster, the friction increases linearly. So we could look at this system and set up a very simple torque balance equation. That is to say, really, the rotational version of F equals ma, right? So if we're talking translationally, then applied force equals, well, mass times the acceleration of the thing that we've applied the force to. Rotationally, the equivalent statement is that the applied torque is equal to the moment of inertia, not the mass, times the angular acceleration. And so, all that we have here is some applied torque, and we have some friction. And so our torque balance equation looks rather simple. We're going to use the convention that friction is in the opposite direction of torque, and we'll say that the direction of torque is positive, just by convention. So we'll say that our applied torque minus the torque from friction, b theta dot, is equal to moment of inertia j times angular acceleration, theta double dot. Every year I forget until I'm giving this lecture that I'd like to. Are people familiar with dot notation? Yeah, I see some heads, some. Okay, so let me just remind you, the dot notation is just used to indicate time derivatives. So one dot means d theta dt, two dots means second derivative of theta with respect to time. This is Newton's preferred notation for indicating time derivatives. Leibniz would have d theta dt here. Lagrange had his own way of indicating these things. They all kind of mean the same thing. These are relatively common in your more sort of physicsy classes. There's so many time derivatives that it's handy to have just a short way of indicating that. Okay, but that's all that that indicates. So this is a very simple torque balance equation, right? Applied torque minus friction equals moment of inertia times angular acceleration. But we can also, as we've talked about previously, we can think about the motor as an electrical system. And I'll just remind you, this is a picture from our lecture about the noise within DC motors, that a decent model for a DC motor is a resistor in series with an inductor in series with a generator. The resistor is there because there's some resistance through this motor, right? The inductor is there because you'll remember from our conversation about DC motors that inside of these motors there's an armature, a loop of wire through which we pass current. And that wire lives within a static stator electric field. So when we put current through there, it feels a torque. And that's what makes the motor actually spin. But there does exist some inductance associated with that internal mechanism. So there's an inductor in series there. And then there's a generator, which represents the back EMF from the motor. When the DC motor is spinning, what we have is a spinning coil of wire inside of a static magnetic field. That is a generator. So as the motor spins, it also behaves like a generator and generates a back EMF. But we could look at this, and this too, we could come up with a differential equation based not on the mechanical properties of the motor, but instead on these electrical properties. So instead of setting up a torque balance equation, we can generate a differential equation based on Kirchhoff's voltage law. So we know, by looking at this diagram here, that our applied voltage minus the voltage drop across the resistor minus the voltage drop across the inductor minus the back EMF is equal to 0 by straight up Kirchhoff voltage stuff, right? So that is to say applied voltage minus voltage drop across the resistor, Ri by Ohm's law, minus the voltage drop across the inductor, LdI dt, minus the back EMF is equal to 0. Now we're going to go back in a moment here and revisit some of these, think more carefully about some of these terms so that we can make some substitutions. In particular, we're going to revisit that EMF and think a little bit more carefully about how do we actually write that down as a function of some of the other things in this equation. But for the time being, this is what this looks like, right? So at this point, we have a very simple differential equation that represents the motor mechanically. We have a very simple differential equation that represents the motor electrically. And what we're going to do by revisiting some of these terms and making substitutions is combine the two into a coupled set of differential equations that represents the motor as an electromechanical system, a system that includes electrical state, current, and mechanical state, things like, position of the rotating propeller, for instance. So let's do that. And let's think a little bit about this back EMF. I'm waving my hands at this a little bit, but perhaps it stands to reason that if you think about the motor when it is not operating at saturation, that's to say, it's in its sort of, we don't have it on full blast, then there's approximately a linear relationship between the applied voltage to the motor and the rotation rate of the shaft. So that is to say, the rotation rate of the shaft, theta dot, the time derivative of the angular position of the shaft would be its rotation rate, is related to the applied voltage to the motor by some constant of proportionality that I'm just calling K sub V. It's just some number. That is just to say that the rotation rate of the motor when we're not in saturation is linearly related to the applied voltage. So what we have here is a linear equation that relates voltage applied to the motor to the speed of the motor. And as it turns out, if we rearrange this equation, we can get one that instead tells us about the back EMF generated by the motor as a function of its rotation rate. So in other words, this linear relationship sort of holds in both directions, right? So what this tells us is that back EMF is equal to 1 over that constant times our rotation rate. 1 over that constant is just another constant, so let's just give it a name so that we don't have reciprocals in here. We'll just call it K sub E. And so now we have this nice expression for the back EMF that is a function of the rotation rate of the motor. Back EMF is equal to some constant times rotation rate. It's linearly proportional to the rotation rate. So we could substitute back into our Kirchhoff-based differential equation that represents the electrical state of the motor, substituting in for that last term. So now instead of minus V EMF, we have minus K E theta dot is equal to 0. Like I said, we're figuring out how to tie these two things together. And so we're looking for opportunities for these two differential equations, the one representing the electrical state of the motor, the other representing the mechanical state, to share some state so that they become coupled. So let's revisit another term. Let's think now about, if we go back to our picture of the mechanical model of the system, we talked about there being some torque applied to the shaft. Let's think a little bit more carefully about that torque. We can make a similar substitution here. If you think about that torque, you'll remember, again, from our discussion about these DC motors, is the source of torque in these DC motors is the fact that we have current, electrical current, running through some armature, a loop of wire, that exists in a static magnetic field. And if you think back to, one of your introductory physics classes, you'll know that a current carrying conductor in the presence of a magnetic field will experience a force, right, or a torque here. So that is to say that the torque felt by the shaft is linearly related to the current running through the armature. And so very much like the equation that we were looking at above, we could say, the torque that we're experiencing is equal to some number, kT, some constant, times I, the amount of current actually going through the motor. So we could make this substitution back into our mechanical differential equation for the system. So we've just substituted kTi there for torque. So now we have torque as a function of current. So we've got a sort of electrical thing here in our mechanical model for the system, right? And in the electrical system, that theta dot gives us a sort of mechanical thing in our electrical model, and we can tie the two together. And as it turns out, so we've got these two constants here, one proportionality constant that relates torque to current, another proportionality constant that relates back EMF to rotation rate. As it turns out, if you are using SI units, those two constants are about the same. It's the motor constant. And so rather than having K sub T and K sub E here, we can just say K, the motor constant, which allows for us to write the final version of these two differential equations. The first one, our mechanical model of the systems, becomes K, the motor constant, I, that's our applied torque, minus torque from friction, B theta dot, is equal to moment of inertia times angular acceleration of the shaft. And then electrically, by Kirchhoff's law, we know that applied voltage minus Ri, the drop across the resistor, minus L di dt, the drop across the inductor, minus K theta dot, the back EMF generated by the motor, is equal to 0. And here now, we have a set of coupled differential equations that describes our DC motor as an electromechanical system, a system with electrical state and a system with mechanical state. What we are really interested in, if we think about this motor as an input-output system, the input here is V, the voltage that we apply to the motor. Perhaps a little bit more precisely in our case, it's the duty cycle of that PWM signal that we send into the motor, but the motor sees the average of that, of course, so it sees some input voltage here. The output of our motor is its rotation rate. Perhaps we could think about the rotation rate as being theta dot, the time derivative of the angular position. What we'd really like to do is generate a transfer function that describes the translation from applied voltage to motor rate so that we can study it using things like Bode plots. And we could look at that Bode plot and evaluate the stability of the system and think a little bit about how we might augment the system by way of feedback control. So in order to generate that transfer function, we will take both of those differential equations and Laplace transform them. Is this something folks have seen before? Laplace transforms in one or another class? I imagine so. Maybe it's been a little while. I'll just remind you that the great thing about doing Laplace transforms of differential equations is it takes differential equations and it turns them into algebraic equations. And so it turns differential math into algebra, which is relatively easy. And I'll just remind you too that generally the convention is that we represent the Laplace transform of some time varying signal, say I there. You could imagine that really being I of t. I is a function of time. The Laplace transform of that becomes represented by the capital letter I times the Laplace unit here, this sort of complex frequency domain value s. So the Laplace transform of I becomes capital I function of s. And I'll remind you also that when we take a Laplace transform of a time derivative, we end up with a leading s out front. We take the Laplace transform of a second derivative, we end up with an s squared out front. Right? So the Laplace transform of that first equation, ki minus b theta dot equals j theta double dot, becomes k Laplace transform of I minus bs Laplace transform of theta is equal to s squared j Laplace transform of theta. You now have an algebraic equation. And we can do the same thing for the electrical differential equation here. So we end up with two Laplace transforms. With these two Laplace transforms, we can algebraically rearrange them to generate theta dot. That should say, yeah, okay. Let's define s theta s as equal to big omega s. That is to say, you know, the Laplace transform of the motor rate here as big omega. We can generate the transfer function that takes us from applied voltage to motor rate by simple algebraic rearranging. We end up with the following transfer function with a lot of constants in here, right, and some s's and so forth. With this transfer function, we can apply, you know, all of the standard analysis tools to this thing, things like Bode plots, which is what we're going to look at here in a moment. So what I'm about to show you, let me just ask before I do. What I'm about to show you is the Bode plot for this transfer function. Bode plot, I'll again remind you, generally it's composed of two pieces. The top shows the amplitude response of our system. The bottom shows the frequency response of the system. Before I show this to you, does anyone have any intuition for what we should expect for this to look like? Remember, this is showing us how the motor translates voltage to motor rate. Yes, exactly. In other words, what you're sort of describing here is a low-pass filter. The observation is that if we slowly vary the voltage that we're applying to the motor, maybe by way of that duty cycle function generator knob, slowly turn it back and forth, what you hear and observe the motor doing is speeding up, slowing down, speeding up, slowing down. It's tracking your input. But you could imagine that as you go faster and faster and faster and faster, say, for instance, you're changing the applied voltage 1,000 times a second by way of a PWM input, the motor does not turn on full blast and then turn off 1,000 times a second. Instead, it averages that input. It low passes the input. And so we'll look at this in a moment, but perhaps it stands to reason that we should kind of anticipate a Bode plot that looks like a low pass filter here. To offer you another analogy, let's think about a different kind of motor for a moment. Rather than thinking about a little DC motor, think about the motor in your car. Let's say it's an internal combustion engine in your car. And you could imagine that if you're driving the car and you slowly push the gas pedal down and then slowly bring the gas pedal up, the car will accelerate and decelerate and accelerate and decelerate. However, don't do this, but if you were to go right, really fast, the car doesn't go really fast, stop, really fast, stop. Instead, it kind of averages out what your foot's doing. An analogous situation is happening here. So when we look, let's actually look at this Bode plot now and think about it a little bit. This is the Bode plot for the transfer function that we were just looking at, and as we kind of expected, what this looks like is a low-pass filter. So we see that at low frequencies, our amplitude response is pretty much flat. And then once we get past our cutoff frequency, which is somewhere around the hundreds of radians per second or so, it rolls off. And about at that cutoff frequency, we see about minus 90 degrees of phase. Out at high frequencies, we see minus 180 degrees of phase. So that is to say that rolls off at about minus 40 dBs per decade. So it looks like a two-pole low-pass filter. Note, just incidentally, because we're going to come back to this in a moment, the cutoff frequency for this is pretty high. It's like hundreds or so of radians per second. As we'll observe here in a moment when we look at the transfer function for the pendulum is, its cutoff frequency and so forth is at much lower frequencies. So from the perspective of the pendulum, the motor looks basically instantaneous. Okay. So that was a discussion about this block here. I'd like to now have a discussion about this block here, the pendulum physics. So let's just think quickly about that pendulum. Oh, and by the way, the step response to the motor, right? So step response being you're applying no input to the motor, no volts, and then you step it up, right, to like, I don't know, a volt or something like that. What does the output of the motor look like? Given that the motor looks kind of like a low-pass filter, perhaps it stands to reason that your step response looks kind of like this. The motor doesn't instantaneously snap up to its final rotation rate. Instead, it creeps up, like you would expect a low-pass filter to do. Let's see. So now we can think about the pendulum, and we can go through a very sort of similar set of analysis here. There's only one extra little bit of trickiness associated with the pendulum that I'll come to in a moment. All of the equations that we were looking at above were linear. Pendulum, it turns out, is nonlinear, so we'll have one extra linearization step. But in much the same way that we set up a torque balance equation for the mechanical model of the motor, we can also set up a torque balance equation for the pendulum. So we're going to think about the torques that are acting on the pendulum, and in fact, there are three. There's the torque generated by the thrust of the drone motor to actually lift it. There's, of course, torque generated by gravity, right, trying to swing it back down. And then we also have torque from friction. So let's think first about that torque from the motor. And to an okay approximation, right, we could say that the torque from the motor is equal to the force from the motor times the length of the lever arm. Think back to like your first physics class, you know, torque is force times distance from lever arm, right? We're making the assumption here that the motor orientation is orthogonal to the direction that the pendulum is rotating, right? Which is how we've actually put it in. So there's no sine or cosine term here for that reason. So what's the force from the motor? Well, the force from the motor is linearly related to the square of the motor speed. So if omega here is the speed at which the motor is rotating, the force out of that motor is equal to that speed squared times some constant of proportionality. And then L is just the length of the motor. So you go, it's nonlinear. Okay? This is part of what makes this a hard control problem, just by the way, is that square sensitivity for your force means that as you come up and your sensitivity to the torque that you are getting from the motor increases, this makes this a tricky, interesting control problem. Okay, so that's the torque we're getting from the drone motor. We're also, of course, getting torque from gravity. The torque from gravity does have a sine term here because, of course, gravity is always acting, the force from gravity is always acting down towards the center of the Earth. And so as the arm rotates, there's a sine theta that appears here, where theta is describing this angle from vertical, right? But that would just be mg, the force from gravity, times L. I'm making a little bit of an assumption here that almost all the mass of the pendulum is out at the end. It's an okay assumption, given the shape of this arm and so forth, but okay. So it's force from gravity, mg, sine theta, the component in this direction, times L, the length of the motor arm. This would be the torque that we're getting from gravity. And then, of course, we get some torque from friction. And much like our earlier model for friction, we're just going to say torque from friction is linearly related to the speed at which the arm is actually turning. So with these three torques, we can set up our torque balance equation, just like we did previously. Right? We know that the sum of all our torques is equal to the moment of inertia of the arm times the angular acceleration of the arm, theta double dot. We make a simplifying assumption here just for purposes of this conversation. We'll say that the beam mass is negligible compared to the mass of the motor at the end. It's an okay assumption. Right, and then we can just set this up. So we say our torque from thrust minus our torque from gravity minus our torque from friction is equal to our moment of inertia, ml squared, if we make this assumption that almost all the mass is at the end of the arm, times theta double dot, the angular acceleration of the arm. We can substitute in the expressions that we just found for each of these torques from thrust, from gravity, and from friction to end up at this equation. And then what we're really interested in is the angular acceleration of the pendulum. So we rearrange this to solve for theta double dot, and we end up with the following equation, which I mentioned is nonlinear. We've got a sine theta here, right? We've got an omega squared here. We've got a nonlinear equation. It would really be handy for this to be linear, because then we can do things like make Bode plots and look at them and think about stability and talk about them and so forth. So what we're going to do is cheat just a little bit, and we're going to choose some orientation of the arm and linearize about that orientation. And we could choose any orientation that we wanted to for this analysis. For purposes of this conversation, I'm linearizing about the arm hanging straight down, in part because I think that is perhaps easier to physically intuit, the behavior that you should expect if the arm is hanging straight down and we turn the motor on a little bit or something, right? So let's do that. How do we linearize this nonlinear equation? Well, we do a first order Taylor series expansion. So we have our nonlinear equation for the angular acceleration. We say, okay, given this, let's consider the equation for theta dot plus some small deviation. And you'll remember, right, that doing this suggests that we evaluate this function about the point which we are linearizing. And for our purposes here, we're assuming that the motor is spinning at some relatively slow rate. Maybe it's hanging, here, just spinning a little bit at some omega naught. We're supposing that the arm is hanging at some theta naught angle, 0-ish. And we're assuming that the arm has some speed that we're linearizing about, which is 0. The arm is stationary. Okay. So we evaluate our nonlinear function at the point where we're linearizing, and then we take a first partial derivative with respect to each of our variables here, right? And evaluate that partial derivative at the point where we're linearizing and multiply by that small deviation. This is just a Taylor series expansion with the first term of the Taylor series for each of the degrees of freedom here. So okay, and then of course we can subtract out all of the constant stuff here to end up with a linear equation that just represents small deviations from the point about which we've linearized. So now we have little deltas, and we find this expression, a function of the derivatives of the partial derivatives here. And those partial derivatives are not so hard to take, right? We look at this equation, and it's not so hard to take the partial derivative of that with respect to omega, for instance, or with respect to theta, or with respect to theta dot. So we take all those partial derivatives and evaluate them at this point, omega naught, theta dot naught, to end up with the following expression. And then, like I said, we are going to linearize about an angle theta naught of 0. So we substitute that in to end up with a linear differential equation that describes deviations from some set point. With this linear equation, we can now do exactly what we did for the motor previously, which is Laplace transform this thing and generate a transfer function. In this case, our transfer function takes as an input the motor rotation speed, and as an output, it generates an arm angle. And that looks like this. And this too, if we consider this transfer function in isolation, we can think about its Bode plot. Think for a moment about what you expect this transfer function to look like. A transfer function that takes motor rate as an input and gives you arm angle as an output. This one looks a little bit more interesting. It looks like the following. Where what we see is our amplitude response is relatively flat. There's a resonant peak, and then this rolls off at about minus 40 dBs per decade. We see a phase. We accumulate minus 90 degrees of phase at the resonant peak, and then out at high frequencies, we've accumulated minus 180 degrees of phase. Remind you again, we're linearizing about hanging straight down. And we've talked previously about how beneath horizontal, this is a relatively easy control problem because it's a stable system down beneath 90 degrees horizontal. That stability is evident on these Bode plots. So we could look at this, and does anyone remember gain margin and phase margin? Do those terms ring a bell for any folks? Let me just remind you. So the phase margin, in order to figure out what our phase margin is for some system, what we do is we find the point at which, actually my amplitude here makes it a little bit tricky. So this is stable because we're always beneath 0 dBs. But what we would generally do is you find the point at which your amplitude response crosses 0 dBs. You come down to your phase plot and you ask, how far away am I from minus 180 degrees? That difference is your phase margin. I'll show you, we'll be able to observe this on a Bode plot here in just a moment. As soon as that phase margin drops to 0, your system has gone unstable. Why? Because you have greater than 0 dBs of gain, that is to say you have some amplification at minus 180 degrees of phase. Minus 180 degrees of phase, what that means, if we think about our feedback loop here, with minus 180 degrees of phase, that's a sign flip right there. And so if we have greater than 0 dBs of gain with minus 180 degrees of phase, our negative feedback loop becomes a positive feedback loop. And instead of driving error to 0, we amplify it. So we can use this idea of gain margin and phase margin and look at the Bode plots to figure them out to gain a mathematical understanding of the behavior that you all will observe in lab this week, which is, for instance, turning up the proportional gain and seeing the system get faster and bouncier and then going unstable. We'll look at this in a moment, but you can observe this happening on these Bode plots. So let's scroll down here, and I'm going to wave my hands at this a little bit, but okay, here's our Bode plot for the linearized pendulum. By the way, you'll remember from probably one of your first physics classes that you can relatively easily solve for where that resonant peak must be, root g over L, the length of the pendulum. You could also find out experimentally by observing the traces coming out of, for instance, your accelerometer, poke the pendulum and allow for it to swing, and measure the frequency at which it's swinging, and that's going to be your resonant peak, right? That's the characteristic frequency of that system. Very easy to find experimentally. Okay. So now we have a transfer function for our motor that goes from voltage to motor rate, and then we have a transfer function for our pendulum that goes from motor rate to arm angle. One of the advantages of this transfer function kind of analysis is we can smush those two together, and we end up with one big, nasty transfer function that goes from applied voltage to arm angle. Through this motor, through this pendulum physics, right? It translates all of that. This is what I'm going to wave my hands at a little bit. Oh, let me show you first of all. Here's the step response for the motor, or I'm sorry, for the pendulum, right? So the motor's not spinning. We turn it on very quickly. What does the arm do? Well, perhaps it stands to reason that it kind of goes doing, like that. So that's what we observed there. With these two transfer functions, like I said, we can smush them together. We end up with something big and nasty, but whatever. It's just a bunch of terms. Many of them are constants. We can substitute different constants for a lot of these combinations of constants to end up with a relatively tidy transfer function. And yeah, okay, there's a lot of numbers to plug in here, and maybe you have to figure some of these out experimentally. But okay, we end up with some transfer function that takes us from applied voltage to motor or to arm angle. And just like our other transfer functions, we can generate a Bode plot for this. And what you can see here is essentially the combination of the two Bode plots that we were looking at previously. And I mentioned previously that when we were looking at the Bode plot for the motor, we noticed that its cutoff frequency was kind of high. It was like up in this neck of the woods, around like hundreds of radians per second. The pendulum, on the other hand, its resonant peak was down here at like less than 10 degrees per second. And so you can see that the frequency and amplitude of response of the motor lives mostly out here at the higher frequencies. And down here at the lower frequencies, we see mostly the contribution from the pendulum. But here, we can look at this and ask questions about things like stability by looking at things like phase margin and gain margin. So here, let's see. What's our gain margin? Well, to find our gain margin, we would find the point on our phase plot where we cross minus 180 degrees of phase. Maybe it's like here-ish. And then we go straight up to our amplitude response plot, and we ask, how many dBs away are we from 0? And in this case, you can see that we're at like, I don't know, maybe minus 90 dBs. So that's a very stable system. We are certainly not amplifying anything at minus 180 degrees of phase. This sort of, right, is the system that this is the open loop system that you're starting with. And what I recommended as a tuning process was that you start by adding proportional gain. Proportional gain does not affect our phase plot at all. All that it does is lift our amplitude response up and up and up and up. You could imagine that as we lift this up, right, we're going to eventually hit that 0 dB point. We'll hit it first at that resonant peak, and then as we lift it up, that 0 dB crossing moves out and out and out and out and out. And eventually, our gain margin drops to 0. So we can look at this. Open loop step response, yes. So we can look at this, and let's consider just proportional gain. Okay, here, I've added a bunch of proportional gains, so you can see our amplitude response plot now goes up above 0, right, and back down. And here, now what's our gain margin? Well, now, if we cross minus 180 here-ish, we're very, very close to the edge of stability. What this looks like in our step response is lots of oscillations. What this looks like in the lab is this. This is the consequence of increasing just proportional gain too far. There it is, the Bode plot response. Here it is, the phenomena actually being observed in lab. It gets bouncier, it gets bouncier, it gets bouncier, and then it goes unstable.
I kind of learned how to do this based on like a system that's like not a real system. Like the proportional tuning, the way I understand it is that you try to get it to oscillate around what you want, and then you use like D to get it to like stick there. Is that how it is?
Yeah, that's largely what that's a very similar process to what I'm describing. Yeah, yeah, okay.
It's not like that off base, even though it's like in the computer simulation.
Right, yeah, yeah. So by the way, this step response here is with just a smidge of gain margin. So we're stable, but boy, we're getting close, right? There's a lot of oscillation here. As soon as you go above 0 there at your minus 180 degree crossing point, you now have negative gain margin. It's an unstable system, and the step response looks like the following. growing without bound to the extent that the motor is able. What it actually ends up looking like is saturation off, saturation off. But then what we talked about is how do we mitigate this oscillation? We mitigate it with some derivative term. In a Bode sense, what the derivative looks like is plus 90 degrees of phase. The derivative term has some cutoff frequency. It adds 90 degrees of phase. And then beyond the cutoff frequency, it starts adding plus 20 dBs per decade of amplitude response. I can show you a picture of this, I think. Okay, so just the derivative term, if we look at the Bode plot of just the derivative term, looks something like the following. It has some cutoff frequency, right? And then at the cutoff frequency, we've added about 45 degrees of phase, and then beyond it, we're up at plus 90 degrees of phase. When you play with the proportion, the derivative gain rather, the number KD, what you're doing is moving this cutoff frequency around on this plot. If you make that gain extremely large, the effect of that is basically you're moving this to very low frequencies. So what you'll do experimentally is we want to start adding phase where? Well, somewhere like a little bit after the resonant peak here. And so this is a PD-compensated system. This has both proportional control and a derivative control. From the proportional control, you can see that the whole amplitude response plot is lifted. But now with derivative control, you'll observe that we have some comfortable amount of gain margin. We come down here to minus 180, go up there and ask how far are we away from 0 dBs. You can see that the derivative term has basically bent this frequency, or I'm sorry, the phase plot up at the cutoff frequency, increasing our stability at the cost of speed. Slows our system down, but it adds stability. What we want is a snappy system that's stable. The general game that we're playing here is we're trading off speed and stability. And on any system where you want really fast response, you're kind of dancing on this edge. An example would be like a Formula One vehicle. Those are right on the edge of stability because you want as much speed from the response of that system as possible. So you're dancing right on the edge of stability. And you can see it if you watch a race. The wheels sometimes spin a little bit, right? They're right there on the edge. That gives them maximum maneuverability, maximum speed, but they don't want for it to be too stable because that costs them system responsiveness. In fact, I believe it's the case, and maybe some of you know this much better than I do, that the top of the line fighter jets are in fact unstable. They require a very fast closed loop control system to keep them flying stable, because without that, they're actually designed to be unstable. Because they're designed to be unstable, they are wildly maneuverable. You turn, it's an unstable system, it just goes like that, right? So it makes them highly maneuverable, but in order to keep the thing in the air, they got to keep a loop closed around it. But like we talked about, even so here's the step response with a PD-compensated system. You can see we're stable, we've got some overshoot, right? We're stable, but I'm trying to drive this to 1.0 there, and you can see we still have steady state error. In order to get rid of that steady state error, we need to add a little bit of integral gain, because unlike the derivative gain, which adds 90 degrees of phase, the integral gain removes 90 degrees of phase. It destabilizes the system. So we want just a pinch of it. So the Bode plot for a full PID system looks like the following. The whole system is sort of elevated by the proportional gain. We see minus 90 degrees at low frequencies. That is the integral contribution here, right? And then it turns, and we add 90 degrees of phase at higher frequency from the derivative term. So you could imagine that when we're PID compensating our system, we're sort of superimposing this onto our open loop response curves. And by playing with where these cutoff frequencies are, what we can end up with is a fast system that is stable but still responsive, where we get to choose how much overshoot we're going to allow. In our case, a little bit of overshoot is fine, There's lots of control systems where overshoot is catastrophic. Say, for instance, you're trying to land a rocket on a barge. You don't want to overshoot the barge, right? Because you're just going to slam into it. So we're okay with a little bit of overshoot here. And with the full PID compensated system, we can retain the speed of responsiveness that the proportional term offers us. That proportional term is lifting our whole amplitude response up, decreasing our gain margin. We find the edge of stability. That's where we are right on the edge. We add some derivative gain, and we play with that number so that we're start adding phase right at the point where we are adding stability but not sacrificing too much in the way of speed. With our PD-compensated system, for this system, we are still going to have some steady state error. We add a little bit of integral control. That's has a destabilizing effect on our system, but if we add just a little bit of it, it also raises our system type, which decreases our which eliminates our steady state error. So with a full PID compensated system, our step response looks like the following. We get some overshoot, mitigated, so the proportional term slams on the motor, starts rising. The derivative term gets scared and starts to slow the motor down, but we still overshoot a little bit, and it rings a little. We end up with some steady state error, and then over time, the integral term eliminates that steady state error. So this is hopefully a little bit of mathematical justification for what you will be qualitatively observing and tuning in lab. We are doing some random search of these parameters. They mean something in a Bode plot sense, in a stability sense. And by having some understanding of the mathematical background here, it makes your tuning process targeted. Right? You're not just doing a random search. It's informed by what these terms are doing with regard to the stability and speed of the system. Okay, I will be in lab this afternoon. I'll see many of you then. I'll see the rest of you on Friday.